everybody. Today we are now going to discuss further about the aspects of supramolecular photochemistry and the photocatalytic reactions which takes place in the presence of light. So in the previous lecture we were looking at the photodimerization in the case of substituted cinnamic acid, where R is equal to phenyl to start with, and we saw that how we can control the dimerization process and preferably get those kind of products which would not be formed either in solid or in the aqueous solution, but by using suitable host we are able to template them in a certain way that head to head interactions takes place and we get the desired products and sufficiently large yields in cucurbiturils. Now along the same line, let us now further look at some other interesting examples that if we now consider charge groups. So we were looking at for example, we were looking at uncharged systems, but we can also have charges on the systems. We can have a positively charged species here, and we can also have positive charge here as well as positive charge here. Then how are they going to actually come close to each other to dimerize in the presence of a host, for example the cucurbiturils. So naturally in the case of cucurbiturils, as we can see that you have got this molecular vessel, so the positive charge species will always, they will be away from each other so as to minimize the electrostatic repulsion. We can minimize this electrostatic repulsion because if they come together in a way that the positive charges are present, then this is not a favorable orientation. So we can have dimerization in such a way that the head and this is a tail, so it leads to a head to tail dimer. And what if both the species are positively charged? Well, dimerization has also been achieved for systems where protonation happens at both the sides. For example, we have got NH3 plus NH3 plus this species, and when we use cucurbituril H nu and aqueous solution, we are able to achieve dimerization where the positive charges are there, but essentially they are extensively stabilized by solvation with water molecules. And also there is a formation of CC bonds which allows for the stabilization of the compound. So it is the interesting thing is that the resulting product is stabilized by extensive solvation leading to the formation of the product. We can also have the protonation in pyridine based systems, and under similar conditions we can again have the photodimerization where we have pyridinium plus, pyridinium plus, pyridinium plus and pyridinium plus. And if you change now the position of the nitrogen, for example, if you now consider this one N plus H, and this is the para position, this is the meta position which is protonated, then we will have this is N plus H, and here we will have M plus H. So this kind of a product will be formed, that is dimerization takes place, and this is facilitated by pi stacking as well. So dimerization of olefins can take place in the presence of suitable host templates like cucurbiturials. So that talks about the relevance of cucurbiturials as well. We looked previously at the dimerization of coumarin in the presence of the diol compounds, and it has also been found that there are different templates also that can mediate this dimerization of coumarin. For example, there have been a lot of applications of Fujita's nano cage, that is the PD6L6 12 plus cage, the octahedral cage about which we have studied, and here also it has been observed that this palladium cage we have here. So we have the octahedral, and the palladiums are sitting here, and so these are the ligands which are present here. So we have this octahedral cage. Now in this particular octahedral cage, this is the polar part, or and this is the non-polar part. So we can have actually the inclusion of so we have the reactant molecules. So we have this polar part, this is the polar part, and essentially this can now be encapsulated in a large palladium cage. Okay. So see, this is the encapsulation inside the palladium cage, the palladium nano cage you can see, and this is the polar part which is in proximity to the palladium center, and the non-polar part is in the proximity to the hydrophobic part. And now this resulting species is stabilized in water, and then when we irradiate it, it leads to the formation of a dimer. You can look at the stereochemistry. And this gives rise to the head to head syn head to head dimer. So these kind of cages can be formed now, you can see, and these cages can actually stabilize the reactant molecules, and then the form of products are formed. This can also be utilized to perform reactions. Palladium nano cages can also be used for a dimerization of coumarins as mentioned, leading to the formation of the same syn head to head dimer. So this can also be performed. We can actually now do this reaction in the presence of the palladium nano cage to give rise to the syn head to head dimer. So the reactions proceed in a very facile way, and now we can also look at some other applications of solid state photodimerization, where we can consider charge transfer interactions to accommodate the dimerization process. For example, say we have F5 here, we have F5 here, and this can now dimerize on irradiation in the solid state to give you this is F5, this is F5. So this is the dimer, and here you can see that there exist charge transfer stacking interactions which actually drive this dimerization process. You can extend this to longer olefins. So you have the two double bonds here, and we can have F5 here, and then again under similar conditions it can template the formation of structures. Okay. So these are top, then we have this part, and then this part comes down, and then you can have this here. So again you have got favorable pi-pi stacking. There can be some change in the geometry because the carbon becomes sp3 hybridized here, but overall this forms a case like arrangement. So we have this kind of nice ladder motif which is formed. Similarly, it has been observed that we can also selectively protonate one end, that is the pyridine end, to achieve dimerization of olefins. So for example, let us consider this particular reaction where you have the hydrochloride. Now you have protonated the pyridine, and we have the corresponding halogen here, and H nu solid state. So this is the head part, this is the tail part. It will lead to the, so this will become my pyridinium H plus. This is the aryl part, tail part, this is the aryl tail part, and this is my protonated pyridinium, this is the head part. And now there are favorable interactions between this protonated pyridine with that of the aryl group. So this leads to the formation of an anti head to tail dimer. It is also to be kept in mind that the unprotonated compound does not react at all. So we can take another example of this where we extend it to N plus H X H nu solid state. This will now lead to the formation of COPY R CO PYH PYH. Again it forms the anti head to tail dimer. So in this way we are able to have dimerization processes which are activated, and we have also been able to achieve the formation of 4-membered cyclobutane rings by this process in a facile one-step dimerization. Let us take this particular reactant Let us take this particular reactant and it's new, and it has been observed now that it undergoes dimerization. So this is now, we have the phenyl here, and then we have so you can see it forms this 4-membered cyclobutane ring, and it forms the spiro system as well, the dispiro system. So the 2+2 dimerization leads to the formation of this kind of a photoadduct. And photodimerization has also been very useful in achieving chiral induction in crystals starting from optically active materials. So we can start with obtaining chiral crystals using the concept of photodimerization. So let us start with this example: CO2 R1 CN CO2R, its new solid state, and we get CO2 R1 this is the 4-membered ring. This is cyano, this is the ester, and we have got cyano and the CO2R. So we can now see that this particular chiral product has been formed. Okay. So we can now, when R1 is equal to 3-pentyl and R2 is equal to methyl, the enantiomeric excess is 100%. When R1 is equal to 3-pentyl, R2 is equal to propyl, it is 80%. So now you can see in this case we have got an achiral olefin giving rise to a chiral photodimer with 100% E, and this is achieved by topochemically controlled dimerization. So this process, you see, the topochemical control is so useful that we are able to achieve the chiral products from an achiral olefin. And when the crystal structure was determined, it was observed that it crystallizes in a chiral space group, which is a proof of the existence of chirality. On the contrary, when you take these olefins in solution, they simply racemize. So this is a difference. In solid state you have chiral products, but in a solution they simply racemize. We can take another example of chiral induction in this particular compound. should know it is actually the trans product, and H nu pyridine. Sorry. This is my CO2 So you can see here that the reaction happens of this double bond with this particular double bond on the other side. Okay, so the double bond on the pyridine side here reacts with the double bond on the carboxylate side to give you the photodimer in 92 to 95% enantiomeric excess. Similarly, photodimerization has also been achieved on different kind of surfaces like clay, zeolites, silica, etc. One such example on silica surface is you can take this particular compound H nu on silica, it forms you can see that now okay, so you have the favorable pi stacking here. We can get the corresponding trans product as well. So photochemistry, supramolecular photochemistry has also been used to achieve the stabilization of reactive intermediates via encapsulation in large molecules. The encapsulation in large curved molecules. And one such example of a molecule which has got a curved architecture, which can actually stabilize these reactive intermediates, which otherwise in gas phase or in solution are very reactive, is hemicarcerant. So hemicarcerant, the overall shape is like this. This is like it has got this kind of a shape, and this cavity is having both hydrophobic content as well as hydrophilic content, but by and large it's a very compact molecule having a closed shape, and therefore it is able to stabilize reactive molecules. For example, we can have if we have this particular molecule, we can now, in the presence of light, it will form cyclobutane plus carbon dioxide, and this can be stabilized. So normally the short-lived species which actually exist for a few microseconds, they can actually be stabilized for a period of days, weeks or months inside these hemicarcerants. So, for example, cyclobutadiene can be stabilized. Then we can take another example of this is one. Then we can take another example of butene-dione, please keep in mind that we always have the hemicarcerid, that large bulky cyclic molecule which has got a cyclic curvature, and when we irradiate with light greater than 400 nanometer, it forms a species, and then H nu greater than 300 nanometer, it forms benzene. It forms benzene. So you can stabilize benzene inside the hemicarcerid, and you can also stabilize radical species. For example, we can have and this is present, for example, in a cyclodextrin, and we can have the reaction where we will have cleavage of this bond. So it photochemically cleaves. There is a photolytic dissociation in presence of H nu, so it forms this particular free radical, and this free radical inside this cyclodextrin can be stabilized for days. Normally this is stable for a very short time of few microseconds, so it can be stabilized, and similarly we can generate a radical cation. So we can have radical cation which is generated, okay, and then when with this radical cation you can stabilize it for months, okay. So the double bond, you have the 2 electrons, so you remove 1 electron, so you just have the odd electron and this as the radical cation. Similarly you can consider this particular compound, and it can form photolytic dissociation PH2CH dot for weeks, and then if it loses an electron, PH2CH plus, you can stabilize this as well. Another example we can consider is a diazo compound. You have this kind of a cyclic strain system in presence of light in dichloromethane. It forms this particular species, carbenes. It forms a carbene which can be stabilized for days. Inside the hemicarcerid. So we have to keep in mind that all these are being done in the presence of a host, and this association actually inside this cavity stabilizes these reactive intermediates. So overall, as we see, there are a lot of interesting applications of photochemistry, and to summarize, one last very important application of photochemistry is in the field of supramolecular organocatalysis, and I will give you one specific example of a depiction of supramolecular organocatalysis. For example, let us take this particular compound, which is again a derivative of coumarin, and irradiate 350 nanometer, in the presence of a organocatalyst. I'll tell you the structure of the organocatalyst for a period of 2 hours, and it can give rise this particular enantiomer, and then the mirror image of this particular enantiomer okay. So we have the mirror image of this particular enantiomer, and we have this X here, X is here, X is equal to hydrogen, fluorine, YME and methyl, and so these enantiomers are obtained. The possibility exists that these 2 enantiomers are obtained, and what has been utilized is a binapthyl based thiourea as an organocatalyst. So we have this particular structure. We have already seen the applications of thiourea, but this is a modified thiourea where we have electron withdrawing groups here, and we have the binapthyl ring here, and this interacts via hydrogen bonds with the oxygen. So this is the transition state like geometry. So as you can see, this is the transition state like geometry we have. And this comes from the face. So we have now, so when you have the planar phase of the coumarin, the hydrogen bonding is strong from one side of the organocatalyst, and therefore the other phase is now exposed, over which this double bond can come and possible photodimerization can now take place. So here you can see now the photodimerization can now take place in an enantioselective fashion, so that one enantiomer is preferably formed, and what was achieved is specifically when you have CF3 here. So you normally have electron withdrawing groups here, but in this case you have electron withdrawing groups here as well, but you can actually have a different set of combinations, different kind of catalyst with electron donating groups as well as electron withdrawing groups, which will optimize the reactivity of this catalyst. And what was observed is high enantioselectivity was observed in the range of 77 to 96% EE in the photo product when 1 to 10 mole percent of the organocatalyst was used. And it was also observed that this particular reaction can be scaled up to large quantities, and during the process of scale up also the enantiomeric excess is large, almost 96%, and the yield of the reaction is around 77%. So this talks about the power of organocatalysis, which actually is mediated by the hydrogen bonds which bring about the necessary enantioselectivity. So I hope overall in this particular module in this week you have been able to appreciate the relevance of supramolecular catalysis, supramolecular reaction barrels, supramolecular photocatalysis, and all these important and interesting aspects of supramolecular chemistry. In the next week and the last week, we are going to look at some important applications of supramolecular chemistry in other systems as well. Thank you.